Hi, my name is Susan Dumais. I'm the Assistant Director of Microsoft's Research AI Lab, and I'm here today with Michael Jordan, who is one of the world-renowned computer scientists and statisticians in the world. He's been at Microsoft earlier today as part of our faculty summit, whose topic this year is systems and the future disruptions that will be enabled by progress in systems. One of the topics, obviously, in thinking about the next generation of systems is where AI meets systems. So there have been sessions on AI for systems and systems for AI, and Mike has been incredibly involved in some of those discussions. So Michael is the Pei Hong Chen Distinguished Professor in EE and CS at Berkeley. He's also on the faculty in the Statistics Department, and part of a couple of really interesting multidisciplinary labs, one on algorithms, machines, and people, and the other on Berkeley AI Research or something like that. Michael has a background in psychology, statistics, and cognitive science. So he brings a really broad perspective to problems. One of the things that I think is most impressive, Mike, about your background is that you've won a tremendous number of publications, tremendous influence in the areas of computer science and statistics, but your awards come from a broad set of organizations and fields. So you clearly are a fellow of the ACM, but you're also a fellow of the American Statistical Association, the Cognitive Science Society, the Bayesian Society. And I want to start the discussion today by having you reflect a little bit on your graduate work. You were at UCSD with Dave Romelhart and others in the mid-'80s at maybe the second renaissance of the artificial intelligence area, working in parallel and distributed systems. I still have my 2 volumes of the PDP books with the, 3.5-inch floppy disks in the back. Can you say a little bit about maybe the intellectual environment at the time? This field was really nascent. As well as how it's influenced sort of some of your subsequent thinking about problems of intelligence and computation.
Sure. First of all, it's a pleasure to be here. I've known Susan for a number of years. I've been giving lots of interviews the last few years as the interest in the field has picked up. It's the first time I've given an interview to someone who probably knows more than I know about half of the topics we're going to be talking about. Usually you have to be explaining things. So I've moved around a lot in my life, and it's really not directed. It's kind of partly random walk, and it's just because of curiosity and also feeling that not any one person or any one field has got all the answers, and it's by synthesizing various people's perspectives and ideas. And I was thinking about this earlier, how I might explain that. So one of my friends, Jan LeCun, refers to me as the Miles Davis of machine learning, not the Michael Jordan, because he was an example of someone who moved throughout his career just trying new things. And another anecdote was when I was a kid, my grandparents took me to Europe for the first time, and we went to Sweden, and I loved it. And at some point, apparently I was lost. At least they thought I was lost. They couldn't find me for half a day. And finally they found me. I was with a bunch of Swedish children because I decided I'd become Swedish. Because I should just do one thing in my life. I should become a Swedish child. So, I think that I was... first of all, I had a bad American education, and so I was kind of lucky that I arrived at age 20. I knew nothing, and so I could sort of make my own ideas about what to work on. And I think like most people of that age, read some philosophy and found that interesting. And I was lucky enough to be in an era where there had been analytic philosophy. So Bertrand Russell had written an autobiography, and very presciently he was talking about the mind and the scientific perspective on it, and how logic and mathematics and all rose out of the mind, and it just felt right to me that there was something deep about that. And he did it with kind of a sense of humor and a feeling that there was something new going to happen in this area. So that helped to influence me. And then just by hook or crook, what was available to me, I was a program at San Diego, and it was largely because of experimental psychology that I found my first interest. I remember work by people like Roger Shepard, where you talk about mental rotation, and just the idea you could probe into a system that was very, very complicated and still glean things about it from the outside was fascinating. I was just impressed by the skills of people able to do that. I think psychology, though, is just so hard we're probing into a massively complex system. There's nothing else like it. Even think about the economic system of New York City. It's nothing like the complexity of the brain. And think about probing that from, you know, from the atmosphere while you're looking at the lights or the emissions. It's just kind of where we're at. So I still feel that is the field of the future of the next several hundred years. I think it'll take that long to start to really get insights into it. And since I have unfortunately a short lifetime, I thought I'd better move on before to move to faster moving fields. And I think kind of luckily as part of that, I'd also studied some statistics because you had to analyze your data. Right. And I started to appreciate not just the use of statistics and calculating p-values and doing analysis variance, but the 300-year-old tradition of inferential thinking that was embodied in the ideas. And where were those principles coming from and what do they mean? And surely that has something to do with how humans approach the world. So I was already thinking that what's most interesting about humans is their ability to abstract something about the world, and then their ability to deal with all the uncertainty and to make plans and that sort of thing. So I was sort of less interested in the low levels, you know, perception and motion processing, even though I did some work on it. It just didn't feel like where my heart was going to be. So Dave Rumelhart, I'm glad you mentioned him, was my first real advisor in life. He was a brilliant man, genial really. Died young, unfortunately, but he set the stage for much of the work that's going on now. And he also, I don't think, would be happy with just a narrow perspective. He really wanted to think broadly about all the tools and all the ways of thinking. And I really got that perspective. So he, when I first arrived there, was interested in semantic networks and semantics of natural language and perception. And I continue to think those are some of the, you know, the real problems: perception and abstraction, and then how do you think about semantics? I don't think we're there yet. I don't think we understand them. We're very, very primitive in our understanding of those. So then he turned into neural nets, and you know, backpropagation is this famous algorithm, although it's sort of really just the chain rule, and it's got a control theory side to it and all that, and it's reinvented thousands of times. But he really was the person in the neural net field who kind of worked on it for, you know, he reinvented it but for a couple of years. That was his main focus. His office was right next to him, and he'd come in every day telling me about the cool new aspects of what he was trying to do. And he finally got the algorithm, and he tried it out on all the Minsky-Papert problems, and it really did those, and he was super excited about it. So his excitement, his intellectual breadth, and his blend of, there was no disciplinary boundaries for Dave. Experimental psychology, linguistics, mathematics, statistics was all fair game for his intellectual adventure. So I've taken away some of that.
And you talked about descending into fields and sucking up information from them and growing, but you also influence all those fields. And when I look back actually at your early work, your thesis was on learning representations for sequential performance, essentially using recurrent neural networks for some simple cognitive tasks. And one of the things that I remember, it may have been one of your first NIPS papers, was work on adaptive mixtures of experts. Mm-hmm. And that's something that we'll come back to at the end, because I know you have lots of important perspectives on some of the limitations of current deep models. But those cover a couple of really important topics. One is looking not just at snapshots of the world, but at sequences of behavior. And the other is thinking not about isolated competencies, but multiple experts coming together. And it's sort of amazing as I look back at this earlier today that work is, 30 years old now? But it really foreshadowed some of the things that we're seeing today.
Yeah, so thank you for these great questions. I'm not used to getting such great questions. So yeah, I was interested in sequential performance because the neural nets of the day didn't do much sequentiality. It was all about matrices and, you know, factorizations and so on. But I was pretty interested in that in the context of a psychological phenomenon, which was speech. And if you looked at, you know, that's one of the most important sequential acts we do is to speak. But if you look at in detail, you know, all of our articulators, the tongue and the lips and the vocal tract, vocal cords and all, are actually staggered, and they're asynchronous, and they're doing a lot of things in parallel. So the feature vector of the speech apparatus has all the components working in parallel. Nonetheless, there's an overall sequentiality to that. And so it was very much to me, how do you model that? How do you conceive of that? And I felt like things like neural nets were relevant because they were naturally parallel, right? If we can imbue them with a bit of sequentiality, we can get the best of both worlds. We can sort of see a little bit of that. So actually, that was what I was interested in. And I didn't really innovate. Personally, I don't believe very much in the neural network sphere in that particular line of work. Just using sort of recurrent nets, but noticing that if you train them in a particular, very sequential way, they wanted to fill in and therefore kind of do the kind of co-articulation or the parallelism that you would see in real data. And again, that's kind of Dave really liked. He liked that line of work, that the neural net did something that was not part of the training data, but was a reasonably good description of something that was humans were doing. The other line of work, in fact, has gone further for me, which is just thinking about modularity and abstraction, but also thinking about when you have multiple entities that have to cooperate or compete. And it's leading in some of my recent work to kind of much more economics perspectives and thinking about huge numbers of entities that have to work together, not just a small handful like in our mixtures work.
Okay, great. I want to pop from your early days, and it's interesting because you've come back to some of these ideas with several decades of advances in learning and data and in infrastructure. But before I do that, I want to just talk a little bit about some of the fundamental algorithmic and theoretical advances you've made. Your work on variational methods for approximate inference in graphical models is huge. Your LDA paper, I think, has been cited over 25,000 times. The work on spectral clustering, on popularizing EM algorithms. This has really changed, the practice of machine learning and statistics in many ways. Do you have a gem that has not, one of your favorite innovations and breakthroughs is not as well recognized as some of the very popular and widely cited ones?
I'm always the most fond of my most recent work.
Okay.
Because the older work just seems obvious in retrospect and probably even obvious in the day. But no, recent work I think has gone the furthest. It's become more theoretical over time as the field's kind of become more empirical. I think there needs to be a complementary, more theoretical perspective. And so lots of work on optimization and sampling relationships and returning to variational themes. So variational I learned about it from physicists, but I love the kind of history of mathematical ideas, and variational, of course, goes back to variational calculus, and before it says you turn a problem into an optimization problem. So your problem is to integrate, or your problem is to write down a differential equation, and you say, well, how can I formulate that as a solution to an optimization problem? And the optimization problem could be in a space of, say, probability distribution, so your output can be a distribution. But now you say, well, that's a solution to an optimization problem. Having done so, you get brand new mathematical perspective. In particular, you can perturb the optimization problem. That'll then move the solution a little bit. And the perturbation can lead you to insight, but it also can lead you to new algorithms. And so there's variational perspectives on all sorts of things. Calculating an eigenvector. An eigenvector is AX equals lambda x, but it's also a Rayleigh ratio. You optimize a certain ratio, and that is an eigenvector. It's a variational characterization of an eigenvector. Formulating that way, you get new algorithms. And so the physicists were onto this. So people had borrowed the idea of mean field methods from physics into neural nets. And so there was lots of these mean field or deterministic annealing. I found that very provocative, and so started reading deeper. And as often was the case, they had 20 years of history and had pushed that much further, and they started to call that variational methods. And so we borrowed the broader perspective, and then brought that into contact with graphical models. They mainly were studying lattices and physics kind of things, and so we said, well, there's an opportunity to take those same kind of ideas and bring them into the much more structured world of graphical models, and in particular directed graphs. Conditional probabilities rather than just field models. So in some level, it was just kind of explorations in a set of ideas that hadn't quite been brought together, and then EM ideas also. There hadn't been much work on doing them with graphical model, variational kind of things. So, but that still goes forward to this day. That line of work I actually still feel is very, very incomplete. There's hardly any theory on it. There's finally starting to be a little more innovation algorithmically again. It's picking up again. But these things are really long-term projects for not just me, but for the whole community.
You've been doing some work recently on non-convex optimization.
Yeah.
Can you talk a little bit about that? Because a lot of the functions, clearly, that we're trying to optimize, especially in deep models, Or not particularly convex.
Well, not just deep models. So, all kinds of phased retrieval models, all kinds of combinatorial models. A lot of them are non-convex. They have a single global optimum, some of them. So they seem simple, but they have all these saddle points. And the neural nets and all, I think that one of the key problems is they have lots and lots of saddle points. I don't think this was appreciated, at least in my era, back when I was learning about neural nets. It was all about the local optima that you'd fall into and the simulated annealing and ways of getting out of that. And I think it's in the last 5 years or so that it's been realized, well, if there are a few local minima or even a whole lot, there's going to be even more saddle points. And what will happen is at high dimensions, you'll get stuck next to those saddle points for an indeterminate amount of time. And it could be even, scale badly in dimensions, so that if in bigger and bigger problems, you'll spend more and more time around the saddle points. And you won't know that, because when you're in a saddle point, you just feel the learning curve is sort of flattened out. You think you're done, but you really just have yet to escape, find that direction of escape. So let me mention Qi Zhen, who's a student with me working at Berkeley. He's a real leader in this area of saddle point avoidance and escape. And there's a sequence of papers where Qi is the lead author that really dig into this and try to get not just rates of convergence, but dimension dependence. So as I was alluding to, kind of pride in theoretical work, I think this is not just me, but the rest of our field has gotten very good at not just asymptotic rates, but actually finite sample rates. And then beyond that, the constant has dimension dependence, and we're getting the constants. We're getting the dimension dependence. And so that's a theory that becomes extremely interesting mathematically, but also very relevant to practice, and gives this field a lot of connections that didn't exist 5 or 10 years ago. So saddle points are interesting if you want to avoid them. And indeed, there's lots of non-convex optimization problems where it's true. But it's also interesting if you take the game theory perspective, or multiple agents, where you don't want to avoid saddle points, you want to find the saddle points. Because the saddle points are the Nash equilibria, or the other kind of equilibria. And so that's an emerging area that I'm working on with students in my group. There is a literature on how to go towards saddle points, but as is often the case, it's incomplete literature. It didn't face the kind of modern constraints that we have. And in particular, if you create saddle points that are Nash equilibria, you'll probably create lots of other saddle points that you don't want to hit, just because that's how mathematics tends to work. So there's great open problems there. And then if you go to the large scale versions of these things, where you have not just 2 agents or 10, but you've got hundreds of thousands, it's going to be very, very interesting and challenging. So that's one aspect of the economics perspective meets algorithms that I'm very interested in.
Okay, great, thank you. I just want to talk about a couple of other topics. So one is, in the last decade or so, we've seen just dramatic advances in the capabilities of computational systems to do things like understand speech, to understand aspects of vision, label objects, generate captions, to do some aspects of language understanding, particularly the work in machine translation, I think, has been really beyond my expectations. Some work in robotic control. And many of these innovations have fueled, I think, things that neither of us would have expected 10 or 15 years ago. The fact that you can do real-time analysis of voice on phones in noisy environments and get it right a startling proportion of the time. The fact that in machine translation you can translate from one language to another in near real time. These accomplishments have fueled a variety of interesting new computational capabilities. Yet, they have a set of very isolated competencies. And you recently published, I guess it's an op-ed piece or a thought piece in Medium on artificial intelligence, the revolution that hasn't happened yet, that generated a lot of buzz. Can you reflect on the fact that there have been amazing advances, yet we're miles and miles and miles away from thinking about intelligence in the same way that you see in humans, or more interestingly, interacting sets of humans and computational elements?
Great question again. So there's a lot of issues there that need to be untangled, and so I'll try not to speak too long, but my op-ed tries to untangle. I think that everyone has lumped too much into the phrase AI. And one of the phrases I was proud about in the op-ed was that people are using AI as an intellectual wild card. That when they don't understand what's happening or understand how to solve it, they say, AI will do it, or that's an AI problem, or whatever. Most of these systems are pattern recognition systems, and that's great. There are lots of patterns in the world, and these things are pretty good if you have especially lots of labels that help you find those patterns. I, first of all, don't think that's the whole class of problems I'm interested in, or many of us should be interested in. I think that creating systems that serve humans and help us make our lives safer, more interesting, do this at scale, make us able to interact with other humans and the world better. Very few of those have a lot to do with creating artificial humans with speech, language, vision problems. They have to do with all kinds of decision making at scale. They have to do with problems that none of us evolved to solve, that our human intelligence isn't particularly good at, and whereas good decision making inferential principles are going to be needed to build such systems. If you think of domains like commerce or healthcare or finance or et cetera, there's just crying out for here's data, here's utilities of large numbers of players. How do I create something that will work for people? So I don't think that working on what I called in that article human imitative AI, the kind of classical aspiration, which is still an aspiration, I don't think it's necessary for sufficient for working on a lot of these broader challenges. So lumping them all together, I think, is a mistake. The biggest progress has been made in areas like you're talking about, vision and speech and natural language and so on. But the algorithms that are used for that are not necessarily the ones that are going to work for trying to make 100,000 decisions at scale. It is, I think, unfortunate to think that those are the main class of problems that industry should be focusing on. There's a larger class of problems that they should be focusing on. Now, also, I do need to push back. You said the word speech understanding and language understanding and intelligence maybe even have come up there. I don't think these systems, and with all due respect for my colleagues who work in those areas, are doing much speech understanding, right? They're transcribing a waveform into lexical items, right? Very impressively with lots of noise and all that. But they don't understand anything about the speech, okay? Moreover, the natural language translation systems are not understanding the language at all. They are taking in a French sentence and basically they are mapping that string to an English string, all right? And there's no understanding between here and there. Now, when we look at the outputs of these kind of things and the errors and the kind of things they can do, we as humans are able to sort of read into them and say, wow, it seemed to understand something. Well, no. There was a statistical thing that it picked up on, and that's not all it is. That's not, so our ability to understand what's happening in the world, to abstract in particular, we are miraculous abstractors. And neural nets do a little bit of abstraction in their feature finding, but they don't think about the kind of high-level, multifaceted, complex abstractions that humans are able to do.
But I mean, to be fair, a lot of human capabilities, especially perceptual capabilities, are based on statistical regularities of the world.
Well, they could be based on that. We don't know if they are. I mean, so think about a squirrel. You talked about this in the op-ed too. But a squirrel is an amazing perceptual motor system. It hops among the trees in ways that we can even hardly imagine, right? So it's doing somehow its brain has evolved or maybe learned, but probably not learned a lot. Probably a lot of evolution came into making that squirrel so good. So it's able to do things that we can hardly fathom, that our neural nets are maybe starting to approach at the end of our lifetimes. We'll be able to see artificial squirrels. I would hesitate, though, to say a squirrel has a lot of intelligence. Right? Building such a squirrel-like system would require a vast amount of intelligence, our human intelligence. But I hesitate to say that system is going to be one that embodies what I would recognize as intelligence, or understanding of the world, or being able to abstract about it. And I think squirrels, I don't want to limit what squirrels can do. They can probably do some problem solving, and annoy us with their abilities in that regard. Really, so if you haven't seen Doug Hofstadter's thing on, he had an op-ed as well around the same time I wrote mine on the shallowness of Google Translate. And I think he does a pretty good job saying if you don't have any semantics at all, you're just not going to really be able to solve natural language translation. And so you get a sense that people think, well, went from 80% to 90 to 95. Of course, we're going to be to 99.9 soon. Just more hardware, more data will do it. And that just is not true in a domain where it really requires a rich understanding of the world around us to really do it well.
I mean, I think it's really clear that there are huge limitations to the competencies that current systems have. and that to get to the next level, we need to think more broadly about systems that have sort of perceptual or low-level recognition capabilities, as well as more symbolic, deductive reasoning.
Well, they may be symbolic, maybe deductive, they may not. Abstraction is a word that doesn't have to be, the idea that we're having an interview, that's an abstraction of what is happening with all the pixels and all the sound waves in the room right now. And it's not a low-level abstraction, it's quite a high level. There's many, many kinds of interviews and many, many kinds of situations. And all of us humans really understand that kind of thing. I also noticed on the last time I came here to Microsoft, I was participating in an event called the Disruptive Technology Review.
That's right.
Right? And I know what disruption means, but it now has all kinds of other meanings that people have kind of associated with it. It's become a good thing, first of all, and all of us understand that. And disruptive technology review can be parsed in two ways. It could be a disruptive technology review, we're reviewing the disruptive technology, or it could be a disruptive technology review, right? And we all get that, and it's interesting, even funny and amusing.
Yeah.
You probably didn't think about it. You probably picked one of those two, but they're both there. Our computers are very, very far from the ability to understand things of that sense and have humor about them and use them in creative ways and do that not just for the words disruptive in technology, but for about every other word that we can think of. Even the word, like saying that bad is now good and stuff like that. Us humans really, really are flexible with the ability to use that. And that's not even talking about how we interact with the real world and the abstractions that are involved there. So, these aren't problems that one can't work on, but it's just decades. And it's not that we get enough big data sets and enough hardware and we get it. And I just think there's a lot of naivete about that. My colleagues who work on those problems in natural language don't have that naivete for the most part, but a lot of the PR agents for sort of the companies that are doing this do have that naivete, and that's being spread out too far into the community.
Mm-hmm. Can do you have any reflections on what's needed to get to some of the competencies that?
Well, I can give my own. I mean, there's just a huge number. In fact, in some of my talks, I give a long list of challenges for kind of AI. It's not just that you need symbols; you need all sorts of other things. But I mean, I think I'm going to try to avoid your question just because I'm not. I dabble in NLP, but certainly relations and certainly a minimal amount of kind of first order kind of things. Certainly the ability to deal with hierarchies and the ability to deal with abstractions at various levels. But I think we don't really know what we really need yet. So I think it's kind of like someone who was able to, the first people who had gunpowder and could kind of build a very minimal rocket and then could dream about going to the moon someday. Right, and we did go to the moon someday, but there was a whole lot of other new concepts that had to be invented to actually get there all the way to the moon, and so I think we're leaving lots of problems for the younger generation. And even if a neural net could sort of take, it can do like Arabic to English translation at 99%, which again I don't believe that's going to happen. It's going to really at that point be such a huge black box. It's just not healthy for us to turn that over to the next generation and say, here, we're done. We did natural language translation. They're not going to be very happy about that, and they shouldn't be.
So I want to...
Let me just add one more point, because I don't want to come across as negative about this. I mean, this is a great fact that neural nets are an amazingly good pattern recognition classifier system, and that also means you can use these for real-world problems. Right. So the fact that we have, okay but not particularly good translation means that I could probably now take a device, I could speak into it, and out would come bad Mandarin, and therefore I can walk around in China and I can have interactions I could have never had. And that's good for me, it's good for society, it's good for humans, that things like that can be done. Right, but it tends to lead in people's minds way further than that. They think, well, we've almost got natural language translation done, blah, 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 blah. Where does that lead to? And the fact is, well, we're not even close to really, we're like 1% of really being able to do like a human being can do, like a Shakespeare can write Shakespeare, but even like my 11-year-old can interact with his world using natural language.
Well, 18-month-olds can interact with their world in ways that many of our current systems can't do. I wanted to read you a quote from your the AI.
I feel like I'm selling in a courtroom
now.
No,
this isn't. This is a good one, I think.
5 years ago, Mike, you said this, and now you're saying that.
Just as humans built buildings and bridges before there was civil engineering, humans are processing with the building of societal scale inference and decision-making systems that involve machines, humans, and the environment. Just as early building and bridges sometimes fell to the ground in unforeseen and ways with tragic consequences, many of our early societal scale inference and decision-making systems are already exposing serious conceptual flaws. You hinted a little bit at that in your previous comment, but this really focuses on these larger systems issues and systems ways of thinking. Can you comment on some of that, fragility, how we're setting up people to think about what's possible and really what steps we need to take to make progress in some of these areas?
So I really attempted in this op-ed to give engineering the due respect that it needs. Engineering is not just a bunch of nerds playing around with wires, and engineering is really thinking about how to make the world a better place and how to make it a little more predictable, a little more interesting, and so on. So I have great respect for people who did civil engineering, chemical engineering in past generations. In fact, my father was a chemical engineer, and they started with kind of chemical principles that you blend these test tubes together and out comes something, and they went from there all the way to be able to put this together in a factory. And they needed a huge raft of principles to do that, not just the basic chemistry, but all kinds of mechanical things and all kinds of, a range of other things I know very little about. And that took decades to develop. And so I think that's the kind of thing that we're talking about here, but it's even a grander thing. We're talking about bringing humans into it in a very central way, and their utilities and their desires and the conflicts or the cooperation that's involved there. And we're talking about data and so on. So when you start to do that, you realize it's going to be very much decades. It's not going to emerge. AI is not going to happen in 5 years here, and who cares if we get systems that look like humans? It's really about these systems. And so in my op-ed, I tried to kind of come up with very simple examples of problems you might think are already easily solved or whatever, but aren't. So provenance. So database people are interested in a piece of data, not just the piece of data itself, but where it came from, some metadata around it, who did it, when was it done, and all that. And that can be used helpfully in various database systems to make sure something is coherent and consistent and so on. It's much, much worse when you think about learning systems and data analysis and predictions and decisions. So I used an example of medical data that any time you sit down in front of a doctor, they're gonna think, well, they've got some weird symptoms here. Have I ever seen anything like that? And hopefully they read all the medical literature, so they know all the data, but maybe they don't, right? But there's always not going to be a particularly good match between what they see in you and your symptoms and the others, and maybe ideally there's a really good match. But in general, what you're doing is you're taking some somewhat ill-formed ad hoc set of observations that were collected at a different place in a different time, in a different situation, in a different context, and you're making a judgment about how relevant they are to the current situation. It's never going to be the case that the current situation just fits exactly the data you collected yesterday for that particular purpose. All right? So being able to assess the relevance, that data is actually irrelevant, therefore the provenance of that data is not relevant to the situation, therefore I cut off my neural net. I do not let it make the inference that it seems like it wants to make, right? And I need to have my error bars reflect that relevance calculation. Moreover, it's often going to be the case that some data was gathered at some place in time, and it fed through many pathways, and it comes in, and to us it looks like a bunch of independent evidence. And we say, well, I'm seeing 5,000 people were saying this thing, and it was just that someone created the rumor back when. So our political world is full of this, our journalistic world is full of this, and a lot of false positives are happening. People still don't understand much about false discovery rate, that your goal in life shouldn't be to make accuracy high. It should make that relative to the discoveries you're measuring. There's a denominator and a numerator there. Our current systems that do neural nets and all that are doing very, very little with uncertainty. They're doing very little with what-if questions. They're doing very little with the kind of things you need to have in a real intelligent system, even if it's not a super intelligence, do. In fact, they're doing essentially nothing with uncertainty. And so huge gap. So that's kind of the engineering discipline needs to emerge. It's not enough just to know how to put together basic ingredients to build a pattern recognition system. If that pattern recognition system takes in the symptoms of me in the doctor's office and says, you need a heart operation, I'm going to say, what's your error bar on that? Are you sure? Is it 90? Are you 99% sure or whatever? Where's that error bar coming from? Did you know a certain fact about my family? Do you know that other facts about me? Could we think about this what if experiment? Could we get some more data and so on? Those are the things we just can't do at all. But forget even that we can't mimic what a 5-year-old can do in language and all that. We can't do those kind of competencies, about provenance, about multiple decision making, about uncertainty, about and so on. And I just don't see enough people talking about this stuff.
So you're taking a very systems level approach to to thinking about this interesting new set of emerging environments that blend human computation and machine computation. What do you think the right frameworks for thinking about that are? I mean, there's clearly a notion of abstraction. There are, you talked about provenance, the fact that we make multiple decisions, not isolated decisions, the fact that the world is not IID by any stretch of the imagination. In fact, that's probably the exception rather than the rule. How do you start thinking from either a theoretical or an engineering perspective about providing some of those tools? I know you have a little bit of work in that area.
Well, so I think we're going to need a kind of a new Kolmogorov to emerge, or a new Turing or whatever, to really, really break open new things. And whoever she is, it's going to be great. I can't wait. But the best I can do in my lifetime, at least, is as I alluded to earlier, is to not just look within one discipline, not just think that one technique or one way of thinking is the right answer. So I do believe that the vast scope of inferential thinking, of thinking about what's out in the real world and how do I infer that from the limited data I see, including all the sampling patterns that might have gone into it, the biases that might have arisen. Those are ideas that come from 300 years of statistics. Yeah. And it always pains me when I see people that just who are more narrowly in the machine learning world say, well, here's a new problem. We've never talked about fairness before, or bias. Yeah. Well, yes, people have. So if you take the vast scope of inferential thinking and you put that together with the slightly less vast but amazing, computational era of the last 100 years, and kind of the signal processing control theory perspectives, it's already some amazing intellectual challenges in trying to bring those together. And once you do, you get real power. You can have systems that can actually say, with some certain amount of computational resources, I can give you answers that are trustable in a computational sense, but also have got error bars and have inferential. Now, to me, I actually think in my last 15 years of my career, my last third, let's say, I'm going to do my best to bring economic principles to bear with these others as well. So, I do think if you make one decision or a sequence of decisions, that's kind of classical AI and statistics. But if you have to make, your system has to make 100,000 decisions simultaneously, no human being has to do that. So we didn't evolve to do it. But our systems are going to have to do that. And so you need a new kind of thinking. And so economic thinking is not about a single person and their thinking style. Right. It's about large collections, not just of people, but of other entities. And there has been work where there's algorithmic game theory, there's econometrics, where these fields have been brought together, but as usual in very limited ways. So I believe if you bring organizational thinking and together with inferential and computational, already the challenges are immense, and that's what we need to face a lot of these problems. And of course, then you're not done. There's psychological and social and ethical, et cetera, et cetera. Right. But still, just this hardcore of building systems that are economically reasonable in the way they set up incentives among multiple components of the system, and that are able to integrate humans, that humans can have transparency into them, and that they have statistical solidity behind them, not just in there's p-values or error bars, but there's been an appropriate sampling pattern, there's been a design, there's robust, and then that these things will work over time. Yeah. Like the provenance issue doesn't come up if you're looking at one time slice. That's right. Right? Provenance comes up because the data is out of date from it was collected last year in a different city and all that. So, gosh, when just talking all about this, it gets you both excited, but also I think it's daunting, and I think that we have a little bit too much hysteria about how great everything is. We're done. I think the younger people will maybe get this. This is the beginning. It's not a gold rush. It's the start of chemical engineering, but to the power 10. And it'll take decades, and we engage, roll up your sleeves, and try to make sure that we don't overhype and we don't get people going crazy about things like our, superhuman intelligence, which is not going to happen.
Well, machines and humans have complementary skills,
yeah,
and I think at a simpler level, you're talking about sort of massive systems and massive scales and hundreds of thousands of interoperating parts. But
But that's the real world we live in already right
yeah.
now. I mean, think about transportation systems, right? That, you know, all these cars are going around, they're on these limited resources called highways, and there's danger and there's issues. And so if you put that into, I mean, you know, the Uber and Didi and all already do a limited amount of this, but you can easily create congestion, you can create troubles if you don't kind of think about the linked set of decisions that a group of people have to make. And the system has to do that, quote unquote, and that's going to be partly human and partly
computational. Yeah, there's a very interesting world of, I think, hybrid computation systems that we don't know a lot about the principles of, and those systems are now situated in a real world. They're not just in a simulated world or in a laboratory. And I think, you know, as you point out, there are just immense challenges, but also immense opportunities. Let me ask you one last question. You've had an amazing set of students over the last 20 or 30 years. I wrote some of the Yoshua Bengio, David Bly, Emily Fox, Zubin Garamati, Thomas Hoffman, Tommy Yokola, Percy Lang, Marina Malay, Andrew Ng, Satinder Singh, Alice Zhang. More recently, we talked, I guess one of your current students, Aisha Wilson, is joining the New England lab, I guess.
And Lester Mackey's already there.
Lester Mackey's already there, right. And Peter Bodick is already here in Redmond. What advice do you have for the young students getting involved in computer science, machine learning? What should they study? How should they get out of, in many ways, the rat race of climbing up the leaderboard and isolated problems?
You know, I don't have any secrets about it. I just really, every year I'm amazed by how smart these people are and how enthusiastic and entrepreneurial and progressive-minded they are. And I get very, very inspired by that. And I just try to look with each person and kind of look at who they are as an individual and what they've got and what they're missing, and get them to realize that it's going to take 5 or 6 years to kind of, you know, realize what they have inside of themselves. And I tend to encourage them, don't be in a rush. Again, this is not a gold rush. It's not your opportunity to make money. This is not your opportunity to be famous or whatever. It's your opportunity to become a guru. It's your opportunity to study and to actually say something meaningful and deep, and not just say what everybody else is saying, and not try to get ahead of everybody, but just, you know, head off. I often tell them, head off in an orthogonal direction. You see everybody going that way. Appreciate why they're doing it and all that, but appreciate also what they're leaving and missing, and then go orthogonally, and then you can take your own time and you can do it at your own pace, and you can have a lot of comfort with eventually when you start to say things. So a lot of those great students who really have done some great things, they have published a small handful of papers. Now, not all of them. There are some counterexamples who published way more than they should have. But a few of them published a small handful of papers, but they were deep papers, and it was a pleasure to be able to write about how they really solved a big challenge. You know, Aisha Wilson, you know, Lyapunov theory, you know, for continuous dynamical systems that do optimization. You know, Lester Mackey did this amazing work on Stein's method, you know, applied to matrix concentration, even though that was not at all his area, but it was an orthogonal cut in the space that he was taking. He spent a year or two working on it, and something beautiful came out. A handful of those kind of things, and people pay attention. Oh, this is someone who can actually think in new ways and help us to move along. I guess the other point I want to make is that I loved all my students, partly because how great their minds were, but also how friendly and fun they were to be around. So when I pick students, it's kind of an enthusiasm and love of abstraction, of mathematical ideas, of trying to understand deeply, but also humility about each one of our own role in this, and how we being in a social environment and connecting to each other is the best way for all this to work, and it's fun. So I've had a particularly social group. They've all made friends with each other, and I've made friends with them too. And I feel very connected, not just to them, but to a lot of other researchers out in the world. I do travel around to Europe and China and other places a lot, and I easily find myself kind of getting involved in people's lives there, and how they think and what they do, because I think we all are really sharing a lot of this. So I do very much resist the AI is going to be done in this country or that country sort of thing and all. It's really about trade, and it's really about shared understanding and shared development. And I think that the younger people just get that. And so as long as we kind of encourage them that you don't have to give up on that, that you can build a career that is based on sincerity, honesty, and study, and you can. Their natural strengths come right out.
Yeah, I love the reflections on this being giving people space to grow, not feeling like they have to publish 10 NIPS papers in a year, doing it as part of a larger intellectual community. When I think back on the PDP days, there was that sense of energy and excitement, and so I love those reflections. And for new students and thinking about how to get into these areas and to make progress, part of it is to slow down, take a broader perspective, and surround yourself in an environment where you can share ideas, share nascent ideas, and work together to come up to some great solutions. So
yeah.
Mike,
No, and Microsoft is a great, I really, over the years continue to be amazed by how stable it's been as a kind of an intellectual source in the world. And I see Microsoft as kind of returning to the fore right now, just to give a little plug. But
Okay,
I've now been here 3 times this summer. And I think it's really kind of watched the space of IT development throughout the world. And it said if there's a role we can play, and it's sort of almost a senior citizen, but, bring trust back to how, IT interacts with the world. I think that's one of the big agenda items. I think it's being embraced here, and I'm real pleased about that. And so the academic, industry relationship, I think, is very healthy, and Microsoft is kind of helping lead that as we go forward.
No, I mean, for us and for the rest of the industry, I think we need to nurture the kind of students that you and others are developing, and do that together. There are lots of things that folks experience in industry that they may or may not in university. So I think it's a beautiful synergy.
Indeed, I agree.
Thanks for being a part of that with us.
All right, thank you.